Swayam Prabha. Digital India. Educated India.
So, with that background in mind, it provides three kinds of the differentiated services, different classes of the services in the IP networks, particularly guaranteed and adaptive and the best effort service model. So, let's take a look at a picture of how the components of the router would look like in order to provide this kind of the quality of service. In our previous discussion, we understood that the router has got two typical things. One is the control plane and the data plane. And the control plane operation is not real-time operation, and the data plane operations are real-time operations. So what is happening in the control plane? You are constructing the routing table. You use some routing algorithm, bring the information from your neighbors. Utilizing that, you construct the routing table. Basically, that is also called as FIP information. You construct that FIP information. That is an offline exercise. It can run in the background. And in the data plane, the packets are coming and you got a routing table and you are trying to match the incoming packet against the routing table entries and try to make a quick decision as quickly as possible. That is with respect to the forwarding of the packets. But we have brought a second component into the routing router, which is called as a quality of service. So what are the additional things that are coming into the router to provide these quality of service services to the different applications are the following. I'm going to add these many components to the control plane. Specifically, there is a management agent, so using which the application can tell this is my quality of service requirement. The parameters that we looked at, be it the bandwidth, be it the throughput, be it the delay, all of them can be specified through this management agent. And there is a reservation setup model which reserves the resources all along the path across the different routers. And there is also a component called the admission control, which decides when a new flow starts, whether to admit that particular flow or not to admit that particular flow. So if you decide what your application will tell you what is its requirement, you decide whether to admit or not to admit. If you decide to admit, then you reserve the resources between the source and destination two endpoints, and then load this entire information, what is being reserved, what is being the requirement of the application to a database called as the traffic control database. So this traffic control database is consulted by the data plane to make certain choices of the transmission. So you have the traffic classifier which will identify what to do. A bunch of rules are there using which you can decide whether to forward this packet, drop this packet with the priority and all that. And then you have something called in the data plane called as a packet scheduler, which actually picks the packets in certain order from different queues and schedule it for the transmission. And the input for this scheduling decision is coming from this traffic control database. Once you make that reservations and the admission control decisions, and you can tell your scheduler this is what you should do. So taking reference from that traffic control database, the scheduler can pick up the packets from different queues in a certain order to meet the quality of service requirements of different applications. So that is what is all there inside the router when you go with the integrated service architecture. So I said that integrated service model actually uses the reservation. There is a protocol designed for reserving resources inside the network. So that protocol is called Resource Reservation Protocol. In short, this is also called as the RSVP. RSVP does the reservations inside the routers. So if, let's say in this diagram, S is the source or the sender and R is the receiver, and there are a bunch of routers inside the network, and the reservation process starts from the sender transmitting a packet called as the path packet or a path message, and its job is to find out what is the path that is supposed to be taken. So, for example, should I go to router R1, R2, R3, R4 and then to receiver, or R1, R5, R6 and then to receiver R2? I don't know what is the path to be taken. So, if you identify the path, subsequently you can actually reserve the resources. So, the path message originates from the sender, and it identifies a particular sequence of routers to be visited to reach the receiver, and the routers will remember this is the this packet has gone from this from so and so source, and it has come from so and so upstream router and so on. So the actual reservation start in the reverse direction. The receiver initiates the reservation after having received the path message from a particular source. The receiver initiates the reservation of the resources in the reverse direction. So this reservation is telling what is the parameters required, what is the bandwidth required, what is the throughput required in how fashion. So for example, the receiver tells this router that I want a 1 Mbps bandwidth, that is my quality of service requirement, and this router will, depending upon whether it can provide 1 Mbps bandwidth to this receiver or not, you can say either yes or no. If it says yes, it confirms that yes, I can provide you 1 Mbps of the bandwidth. It in turn transmits this another reserve message to the upstream router, and then it asks, okay, I want 1 Mbps of the bandwidth. This router can again decide independently whether 1 Mbps bandwidth can be reserved for this particular transmission or not, and so forth. So the point is, path messages in the forward direction identify the path to be taken, or in other words, what are the places in which you require the resources to be reserved, and the reserve message in the reverse direction will actually reserve the resources for that particular transmission. And the setup or the resource reservation is going to be complete only when all the paths, all along the path from the receiver to the sender, the resources are being reserved. And then the confirmation message is actually sent back to the receiver. Okay, reservation is now complete. You can now start receiving the conversation. The application can actually utilize the transmission, and then it can run using this setup. So that is what the resource reservation protocol all about. An interesting thing about resource reservation protocol is, although in this example this is a single sender and the single receiver are there, and we are trying to reserve the resources for that particular single transmission, it might also happen that more than one receivers are also interested in the same conversation. Maybe if I can call this as R1, another computer here in this space, and R2 is also interested in the same transmission sent by the same sender. Yes. So when the path message is transmitting now, the resources may be reserved for not only for R1 but also for the R2. So if there are more than one receivers connected to a particular router, the router where the conversation or two transmissions are merging, the router which is where the conversation is merging can ask the next upstream router with a requirement which is the sum of the requirements set by or asked by the R1 and R2. It not necessarily always sum, but in some format, whatever is the requirement R1 and R2 are set. So either it can be, if it is a bandwidth, it can be sum of these two. If it is the transmission rate or the delay, it can be minimum of these two, or it can be anything. So it can decide what is the requirement by R1, what is the requirement by R2, and based on that, an aggregate requirement may be sent by the router. Particularly, if this is the setup, this router can set, let's say this is asking for 1 Mbps, this is asking for another 1 Mbps, and together it might ask 2 Mbps. Or it might one of them is asking 1 Mbps, the second one is asking for 2 Mbps. So using the 2 Mbps is the maximum transmission rate. You can also meet the 1 Mbps requirement. So anyhow, both of them are interested in the same transmission. So I can ask a peak rate of 2 Mbps to my upstream router, something like this. So the point is, when the two transmissions get merged, there is a multicast kind of the environment. So the router where the two transmissions are getting merged, the router in charge of that can ask the next upstream router based on what exactly is the requirement in order to meet the two different requirements, what exactly is required from the upstream router. So accordingly, this resource reservation protocol has been designed to meet certain operations. One is the requirements from the different receivers can be heterogeneous. So as we saw in the previous example, R1 is asking for some bandwidth, R2 is asking for some other bandwidth. So you can actually ask it to work with the different kind of the requirements. So it supports the heterogeneity in the quality of service requirement, and it can also support multicast and group transmissions. And interestingly, it is also been designed to adapt to the topology changes. So for example, if my sender is here and the receiver is here, and you have got a bunch of routers in between through which the current transmission is going on, and for some reason if this link is broken and the RSVP can find out alternative path from this source to same destination through some other intermediate router, or by changing the path of the conversation and making a press reservation to meet the quality of service requirement. So at any point of time, because of the link broken or the some new node joining the network, at any point of time, if the topology of the network changes, then the RSVP can adapt to those changes and still maintain the ongoing conversation. And it has also been designed to put less overhead on the routers, particularly with the concept something called as the soft state. It actually puts limited overhead on the router. These are some of the salient features of the RSVP. So let's spend a minute on what are the different messages that the RSVP has got in order to operate, or in other words, in its reservation file, what kind of the message it actually transmits. Two of them we have already seen. One is the path message, which goes from the sender to the receiver to identify the path that the reservation should be done in the reverse direction. And the reservation message goes from the receiver to the sender in the reverse direction along the path of the path message as taken. And the confirmation messages are sent in the reverse direction. Reservation against the reservation request, the confirmation messages are sent. This is the reservation message, and this is the confirmation message to confirm that whatever is asked for has been reserved. And there are occasionally some kind of error message that might pop up. That kind of the message is called reservation error messages. These can be either the path error message or reservation error message. So if the path message cannot be transmitted to the receiver, then the error message that is generated is called as the path error message. If the error is generated during the transmission of the reserve message in the reverse direction, that is called as the reservation error message. It can be either of these two. And the last type of the message that the RSVP uses is something called the tear down message. When you are done with the conversation, when you want to end the transmission, you tell the network that whatever has been reserved can be now released by sending a tear down message. So these are the different kinds of the messages. In different contexts, these messages are used. So with that background, the integrated service model primarily uses RSVP as a signaling protocol to reserve the resources for different transmission. We'll spend a minute on understanding what are the advantages and disadvantages of the integrated service model. So the advantage of the integrated service model is one of the service that it offers is a best effort service that is exactly same as the IP model, the default service model of the TCP/IP. So there is no change that is required to provide this kind of the service model on top of the TCP/IP. So there is no changes that are happening inside your router to provide service. To meet the requirement of the other two classes, you need to bring in the few changes. And for the best effort service, at least you don't have to change any of the things inside the router. The forwarding information base, the way control plane works, the way data plane works, any of them will not be changed. So that is the advantage that you get. And the disadvantage of the integrated service model is sometimes the end-to-end guarantees, particularly end-to-end time guarantees, are hard to predict and meet. So because of some other things, the things might get changed inside, in between two different routers in the middle of the reservation, then it might affect the overall transmission. And the other thing is this reservation model, because you have to, every time you have change in the requirement, new flow is coming, you need to do the reservation all along the path. And already several conversations might be flowing through those intermediate routers. So having an explicit reservation for every flow in the entire path may not be scaling well when you have particularly large number of the conversation going. So providing that kind of explicit reservation for a very large number of the parallel conversation becomes cumbersome. So that's why it does not scale well. So we have alternative models for meeting such kind of the requirements when we have massive number of the parallel conversation and things. Without doing explicit reservations, can I provide the quality of service? So that we will see in the subsequent lectures.